Hello students, welcome back. We completed pretty much everything in section 2 except for the technical proof of theorem 2.6. Here it is. A positive integer n is an even perfect number if and only if, and then the criterion here. And it's a product of 2 to the m minus 1 power times 2 to the m power minus 1, where m is greater than or equal to 2, and this one here, 2 to the m power minus 1, is prime. And this kind of prime is called Mersenne prime. Remember all those? Now, m is greater than or equal to 2, so 2 to the m minus 1 power, this one here, is 2 to some positive integer power that makes n an even integer. As for being perfect, well, that's something we have to work out, isn't it? Part 1 of the proof is the sufficiency of this criterion, the claim that this criterion actually works. And what we have to prove is to prove that n is perfect. N is already even, no problem. You have to prove sigma of n is 2n to prove n is perfect. How do you do that? Well, we have product of these two integers, 2 to the certain power, and then an odd integer, so these two are relatively prime. This vector has only one prime factor, that is 2, and this is odd, so they do not mix. They do not share any prime factor, they are relatively prime. So we can utilize the multiplicative property of sigma to get up to here. Sigma of 2 to the m minus 1 power, which I'm highlighting in blue, can be expressed as a geometric series because the only only positive divisors here are 2 to the 0 power, 1 power, 2 power, 3 power, up to m minus 1 power. Because the only prime factor here is 2, and if there's any other prime factor, then no longer divisor, and then power exceeds m minus 1, that's not a divisor either. So we have 0 power up to m minus 1 power, and we are adding those up. So this is just a geometric series. And this one here is even simpler. This is prime number, so we have only two divisors, two positive divisors, 1 and itself. So 1 plus 2 to the m power minus 1. So we see we have this geometric series, and then 1 plus itself. And then you can use the geometric series formula, 2 to the m power minus 1. As a matter of fact, 2 minus 1, but denominator is 1, so we don't need it. So that's blue. And then after simplification, 2 to the m power only, that's red. And then compare that with original n. What do you get? 2 to the m power minus 1 is common. 2 to the m minus 1 power versus 2 to the m power. So this latter is twice as big as n, so we have 2n. And that's precisely what we wanted all along. And it's perfect. That completes the proof. Oh, by the way, for this computation here, if you don't want to go back to this geometric series, you can always use this product formula, which uses geometric series, but it's okay. We have only one prime factor, so we don't have any of those. Only here, use p is 2, and you're going to get what you want. So we went through the first part. Now let's go to the second part, the necessity. And this is harder, so we have to do it in multiple steps. Step 1 is a preparation. Suppose that n is an even perfect number, and we're going to utilize the first assumption that n is even, and then later we're going to use the second assumption that n is perfect. N is even, so we can express it as the prime factorization of 2 to the s power times other primes. Eventually you get 2 to the s power times t, where t is an odd integer, and as a matter of fact, I forgot this. S is greater than 0. It's an even integer, so s is greater than 0 or greater than or equal to 1. Okay, and then these two are relatively prime. Power of 2 has only one prime factor, that is 2, and then this is odd, so they do not share any prime factor, so they are relatively prime. So we can utilize the multiplicative property of sigma. So decompose, and then as for this, which I just highlighted in blue, we get the geometric series formula again. Because we have prime factors, I keep saying prime factors, sorry. We have factors, or positive divisors, that are 2 to the 0 power, first power, second power, third power, up to s power. So adding them all up, that's a geometric series. So we have geometric series formula like that. And the denominator is just 1, so we get to this. On the other hand, n is perfect. So sigma n is 2n. So sigma n is 2n, and 2 times n is this. So we get 2 to the s plus 1 power times d. So comparing these two have to be the same. Therefore, we get to this conclusion. 2 to the s plus 1 power minus 1 sigma t is equal to 2 to the s plus 1 power times d. Now here, what we claim is these two are the same. T is 2 to the s plus 1 power minus 1, and sigma t is 2 to the s plus 1 power. This is what we want. That's our claim. So sigma is that, blue, and t is that, red. That's our claim. Of course, we don't have a proof yet. We will prove it in step 2, and that's the purpose of step 2. Step 1 got up to here, starting from the observation n is even, and prime factorization got up to this, and then n is perfect, which should give you this, and setting these two equal. Okay, that was step 1. Now let's go to step 2. From the conclusion of step 1, which is reproduced here, we can see that 2 to the s plus 1 power times a certain odd integer is this product. So 2 to the s plus 1 power divides this left-hand side. Okay, so far so good. Now, please recall that Euclid lemma, 2 to the s plus 1 power, and those two are relatively prime. This is power of 2. This is an odd integer. They do not share any prime factor. So 2 to the s plus 1 power must divide sigma t. All prime factors must go here, sigma t. That's Euclid lemma. So that's the conclusion. 2 to the s plus 1 power divides sigma t. Therefore, the sigma t is 2 to the s plus 1 power times a certain q for quotient. And then remainder is 0. So compared with what we want is, as a matter of fact, this blue is equal to this blue, and consequently this red is equal to this red. That's what we want. And then compare that with what we got so far. We got closer. If Q is 1, then we are through. And that's what we want to prove. All right? After step 1, we got up to this, which is reproduced here. And then use this divisibility argument and Euclid lemma to get up to here. And finally, if you prove Q is 1, then you're going to get the claim. Now, in order to prove that, let's put this back into the original equality from step 1, right here where sigma t is it. That's what we have over here. This is where sigma of t used to be, now replaced by the right-hand side here, 2 to the s plus 1 power times q. All good? Now, let's apply some simplification. 2 to the s plus 1 power, divide those out, and we get this. And let's tentatively highlight it in some other color, green. Don't forget this. And then let's move on. Break up the parentheses, no problem. And flip this q to the other side. Again, no problem. Just algebraic manipulation. Just don't forget this one. We are going to have to come back to this. Now, please recall that left-hand side is sigma of t. So the conclusion, sigma of t is equal to t plus q. Let's highlight this into purple. Okay, all right, purple. Now we claim this green and purple imply that q is 1. If not, t has at least 3 divisors, q, t, and 1. Well, t has at least 2 divisors, t and 1, of course, itself and 1, of course, all the time. But why q? Right here, green. q divides t. And then q is not equal to t because this is not 1. Remember, s is greater than or equal to 1. So s plus 1 is greater than 1. This is 2 or bigger, so this is 4 or bigger, so this cannot be 1. So q and t are different. Q and t are always different. How about q and 1? Are they different? Well, if they're different, then q, t, and 1 are all 3 distinct divisors. And sigma of t will be greater than or equal to those 3 divisors because sigma of t is sum of all positive divisors. So just 3 of those will be greater than or equal, sigma t will be greater than or equal to these 3, sum of these 3. But then again, sigma of t is equal to t plus q. 1 plus t plus q versus t plus q. The left-hand side is strictly greater, so what do you get? Sigma of t is strictly greater than itself. That's a contradiction. No real number is strictly greater than itself. So it's a contradiction, and which came from if not. Q is equal to 1. And bingo, that's what we wanted. Q is 1 here, and we get blue. You see, sigma t is 2 to the s plus 1 power, blue. And then back to conclusion of step 1, we get red. And then here, purple. T is 1 now. Q is 1 now, excuse me. Sigma t is t plus 1. Purple. We get these 3 conclusions. We're going to use these 2 to get appropriate expression of n, and this one to prove t is prime. You see, sigma t is t plus 1, and this is sum of all positive divisors, 1 and t, 1 and itself, and nothing more. That proves t is prime. Let's define m as s plus 1. In other words, s is m minus 1, then n is 2 to the s power times t. That's the way we constructed using prime factorization in step 1. And t here, as I'm highlighting in red, is this, 2 to the s plus 1 power minus 1. And if you use m's back here, that becomes 2 to the m power minus 1. And then 2 to the s power is 2 to the m minus 1 power. So what do you have? We get the expression that we wanted. And finally, we have to prove this is machine prime, but that's equal to t. But sigma of t is t plus 1, so it means t is prime. So this is prime, machine is prime. So we have everything, precisely the form we want, and this red is prime. This completes the proof. In the end, yes, we have the necessity and also sufficiency. So much for lesson 10. See you again in lesson 11.